So, yesterday we were discussing some examples of manifold, topological manifold. So, the last example was that of a circle. So, we considered a unit circle, that is the set of points in R2 such that x square plus y square equal to 1. This is set theoretically the unit circle with center at the origin. Similarly, you can think of S2, the sphere. Sphere is set theoretically the collection of triplets in R3 with x square plus y square plus z square equal to 1. You know the shape, it looks like a football. So, collection of all the points on the surface of football constitute what we call mathematically a sphere. S2 means its dimension as manifold remains 2. In general, if you write down Sn, every time you see this is a subset of R2, S3 is a subset of R3. In general, Sn will be a subset of Rn plus 1. So, points on the sphere will be n plus 1 tuples, that is this point of Rn plus 1 such that x1 square plus x2 square plus xn square plus xn plus 1 square equal to 1. So, these are spheres. This is the circle, this is S2 means 2-dimensional sphere, and this is called Sn, the n sphere. We call it n sphere. For n equal to 1, it becomes a circle. For n equal to 2, it becomes a ball, and for general n, it is called n sphere. So, what I will show in general, that all these spheres are manifold of dimension n. So, our assertion is that Sn is a manifold of dimension n. Okay, so this is in fact an example number 5. So, in order to check that this sphere is a manifold of dimension n, first of all we will see whether it is a topological space, Hausdorff topological space. The answer is yes, because it is a subset of Rn plus 1. So, as a subset of Rn plus 1, one can define a topology, subspace topology on Sn, and since Rn plus 1 is Hausdorff, Sn must be Hausdorff. So, it is a Hausdorff topological space. This is an obvious observation. So, for verification, first of all, it is obviously, reason I explained to you, obviously Sn is a Hausdorff topological space. The next is the main task of checking that it is a locally Euclidean space. To check that it is a locally Euclidean space, I will do the following. So, what you do, you consider two open subsets of Sn. One of the open sets I will be calling as U. So, I will take Sn and I will delete from it the point 0, 0, 0, 1. Singleton point is deleted from Sn, and this point is also called north pole. Similarly, you can consider another open set which is obtained by deleting the point 0, 0, 0, minus 1. This one is the n plus 1th place. Here it is also at the n plus 1th place. To see it geometrically, you draw S2 and just look at the north pole. North pole will be this point. Here it will be just 0, 0, 1. You may call it N. And the south pole will be downstairs here. This is denoted by S. It's a point 0, 0, minus 1. Okay. Now U and V are obviously open sets because they are the complement of singleton set. Sn is Hausdorff space, singleton will be closed. So complement of closed is open. So U and V are open. U and V are open in Sn. Okay. Now I have to find a homeomorphism on U and V. So this homeomorphism is a famous map, we call it stereographic projection. So you can see that if you look at S2, this is x-axis, this is y-axis, this is z-axis. So you just draw the xy plane. Xy plane is this plane. Okay. Now what you do, you project these points on the sphere. Consider a point, say xyz. This is a point on S2. I will join this point with the north pole and then will extend this line so that it meets the xy plane somewhere here. Okay? Yes. And then, so I will say the point U, a point in U is mapped to point over here. You may call it P for y. And then I have to suppose this point is U comma V. Is it right? Yes. So similarly, and you can this way you can project all points of the sphere onto this plane. If you want to project this point onto the plane, once again you join it with this point. You join it with the north pole, it will intersect the xy plane somewhere here. So this will be the image of this point onto the xy plane. UV is the image of P. Now one can see what will be the image of the north pole. North pole is already excluded. So the image of the south pole. So you join south pole with the north pole like this. It will intersect at the origin here. Yes. So the image of the south pole under this mapping is the origin. So this way you can project all points of the sphere onto the xy plane. Okay, north pole is not there, so we don't care about it. So now I have to mathematically determine how to obtain UV. So if I call phi of xyz, let me denote the stereographic projection by the symbol phi. So phi of xyz I am saying is UV. So I have to determine UV in terms of xyz. So this is the aim, to determine UV in terms of x, y and z. This is now our aim. That will define phi completely. Same thing in general, instead of S2, if I consider say let us say Sn, then this point will not be x, y, z, it will be x1, x2, x3, xn plus 1 plus 1. And this point will be projected to something, say, it will not be a plane, in fact, it will be Rn. Okay, but I cannot draw Rn like this, so coordinates I can write down. This will be some u1, u2 and so on. Last entry will be un. Okay. So here our problem will be to determine these u1, u2, u3, un in terms of x1, x2, x3, xn plus 1. So in order to determine it, what I will do, suppose this point P divides this line segment in the ratio lambda is to 1. Okay. So I will not write down much. I will just tell you how to get hold of u1, u2, un in terms of x1, x2, x3, xn. So the first thing that I did, I assume that this P divides the line segment n, you may call it something q, okay, q. So P divides the line segment at q at the point x1, x2, xn plus 1. So x1 will be equal to lambda times u1 plus 1 times 0.
So that n will also get 0, 0.
Yes, n in this general case will not be 0, 0, 1, it will be 0, 0, 0, n zeros and n plus 1th entry is 1. So 1 times 0, so nothing, and down stairs 1 plus lambda. Similarly, x2 will be equal to lambda u2 upon 1 plus lambda. And lastly, xn will be lambda un upon 1 plus lambda, and xn plus 1 is also there. That must be lambda times, since n plus 1 and 1th entry is missing, I can assume it is 0. ठीक है ना, मैं u1, u2, un को मैं मान सकता हूँ, ये u1, u2, un 0. So lambda times 0 plus 1 time 1 upon 1 plus lambda. So that becomes 1 upon 1 plus lambda. 1 upon 1 plus lambda. And from here I can see that 1 plus lambda is equal to 1 upon xn plus 1. Okay, now I have to determine lambda also. So from here lambda will be how much? Just subtract 1 from both sides. So lambda will be equal to 1 minus xn plus 1 upon xn plus 1. Okay. So lambda upon 1 plus lambda is there everywhere. So I can see from here what is lambda upon 1 plus lambda, or I can say that it is lambda into 1 upon 1 plus lambda. So lambda is equal to 1 minus xn plus 1 upon xn plus 1. This is lambda. 1 upon 1 plus lambda, xn plus 1. So into xn plus 1. So they are cancelled out. 1 minus xn plus 1. This is the value of, so I have got lambda equal to 1 minus xn plus 1.
So not lambda, lambda upon 1 plus lambda.
Sorry, lambda upon 1 plus lambda.
Yes.
Okay. Now look at this. So this implies x1 equal to u1 into this. So this is u1 into 1 minus xn plus 1. From here x2 is equal to u2 into 1 minus xn plus 1. And lastly here, not lastly, okay, lastly, this is implies xn equal to un into 1 minus xn plus 1. Or xn plus 1 is already there. How much is xn? यहीं लिख दें, इस सब को मिटा दीजिए. So from here xn plus 1 is equal to क्या था? 1 upon 1 plus lambda, क्या निकाला था अभी? xn plus 1. No, इसको keep it as it is. Okay, keep it as it is. So this is xn plus 1. इसको भी मिटा दीजिए, ये वैल्यूज़ हैं. और यहाँ से आपको क्या करना था? आपको करना था सारे यूज़ को डिटरमिन करना था x इन टर्म्स ऑफ x. सो यहीं से लिख दीजिए कि u1 इक्वल टू x1 अपॉन 1 माइनस xn प्लस 1. एंड फ्रॉम हेयर u2 इक्वल टू x2 अपॉन 1 माइनस xn plus 1, and so on. Un equal to xn upon 1 minus xn plus 1. So our map is determined. मैप को हमने ज्योमेट्रिकली डिफाइन किया कि आप उसको देख सकें, और हमने उसकी मैथमेटिकल डेफिनेशन निकाल ली. सो व्हाट डेफिनेशन इमर्जेस? So this implies all these calculation give you that phi of, let me call it this map as phi. So phi is a map which is a stereographic projection. It's a map from U to Rn. Okay. So this map phi is defined as x1, x2, xn, xn plus 1. And this comes out to be x1 upon 1 minus xn plus 1, x2 upon 1 minus xn plus 1, and lastly un is same, xn upon 1 minus xn plus 1. Or simply you can also write it down as 1 upon 1 minus xn plus 1 into x1, x2, x3, xn. So this is how phi is defined. So stereographic projection phi on U is determined. Let me rewrite down its definition. So phi of x1, x2, xn, xn plus 1 has been found. It comes out to be 1 upon 1 minus xn plus 1 into x1, x2, x3, xn. Okay. This is the map. I will call it a stereographic projection, and it is a known homeomorphism. Okay. It's a homeomorphism. Phi is a homeomorphism. This is a known thing, so I will not go into description. Homeomorphism. So what will you say over here? That U phi is a chart on Sn, is one of the charts. Okay, and since it is not covered by one chart, there must be another chart also. So if you consider the union of this U and V together, then you will see that it becomes it covers. So more as Sn is equal to U union V we need a homeomorphism corresponding to V also. Okay. So, if I call, so denote the stereographic projection, denote the stereographic, stereo, REO, stereographic projection on V by psi. So I have to get hold of psi. तो पहले तो ज्योमेट्रिकली देख लेते हैं कि psi कैसे डिफाइन होता है. तो psi का भी वही मामला है कि अगर मुझे किसी पॉइंट की इमेज ढूंढनी है, मान लीजिए इस पॉइंट की इमेज ढूंढनी है अंडर psi, तो v कैसे निकाला है आपने? v निकाला है इस साउथ पोल को डिलीट कर दिया. तो साउथ पोल से उस पॉइंट को मिला दीजिए. मान लीजिए पॉइंट P मेरा यहाँ पे है, तो मैं P से साउथ पोल को मिला दूंगा एंड देन आई विल एक्सटेंड दिस लाइन सेगमेंट सो दैट इट मीट्स द XY प्लेन और RN, whatever you have chosen. So this point Q is called the image of P. इस पॉइंट की इमेज चाहिए अंडर psi, so once again you join it with the origin. It will intersect over here. So this is Q now. This is P. So the image of P is Q. Still it lies in XY plane for S2, in general for Rn. So this is how stereographic projection from south pole is defined. Okay, in the same manner. And the definition will come out to be, once again you can see that the image of the north pole under this psi will be the origin 0, 0, 0. So psi, one can check a projection on V is denote this. Psi will, you can check in the same manner that psi of x1, x2, x3, xn plus 1 will come out to be equal to 1 plus xn plus 1 and x1, x2, x3, xn. So this will be the second stereographic projection, which is also a homeomorphism. Its inverse can also be computed and both of them are continuous. This is a 1-1 map. It is continuous, inverse of.
Minus sign will not come here.
No, here it will be 1 plus because it is minus 1. Okay.
Oh, actually that is minus. Okay.
So minus 1,
So minus 1.
1 is deleted. So that is why it will come out to be this. So these are the stereographic projection. So now what is the conclusion? That Sn has an atlas. So the atlas on Sn is, let me call it A. So this is U phi and V psi. Okay, and every time you are mapping open set into where? Into Rn. So this implies that Sn is an n-dimensional manifold. N-dimensional manifold.
The for circle sphere we can do this also.
Same thing, yes. So in particular circle, our circle is a one-dimensional manifold. You can check it up by stereographic projection or by canonical natural projections also. S2 is a two-dimensional manifold. In general, Sn is a n-dimensional manifold. All right. Okay. So this was example number 5. Now the next thing that I will talk about is all right. Now so let me recall the definition. A manifold is a Hausdorff topological space with the provision that every point has an open set U around it. If I look at a point P, then it will definitely have some neighborhood u which is homeomorphic to an open set phi u. This is some open set in Rn, it is phi u, and this map is phi. So what happens is that u phi, you call it a chart. So the remark over here is that by virtue of the homeomorphism on u, the neighborhood u gets a coordinate system. Okay? So given a chart u phi on a manifold M whose dimension is n, suppose. Okay, given a chart u phi on a manifold M, the homeomorphism phi gives rise a coordinate system on u. We call it a local coordinate system because global coordinates are available only on Rn. On arbitrary topological space, we cannot talk of coordinates, but if it is a manifold, there will be some local coordinates. How they come, that I will explain. So given a chart, one can obtain a local coordinate system. So look at this picture. So this is our manifold M, and I have considered a chart u phi. So look here, so this set is a subset of Rn, and on Rn I have global coordinates. You denote those global coordinates by xi. Now this time I will be denoting by ui. So what ui does? Coordinates of Rn are continuous functions, and how do they behave? They are maps from Rn to R, and they are defined like this. Ui operating on A1, A2, An will give you Ai. Ith coordinate behaves like this. Okay, so ui's are available to me. I will compose these two maps. So the composition of this will be ui composition phi. So this is a real valued function. For each I, ui composition phi is a real valued function on u, and therefore I can consider it as a coordinate function. So I will denote it by xi. Okay. So this gives rise a coordinate system xi on u as xi, defined as xi equal to small ui composition phi. Okay. So every chart has a coordinate system around it. Okay. And these are called local coordinates. So xi's are called local coordinates.
So I running from 1 to n.
Yes, coordinates.
For every chart it will be xi.
Yes.
For every chart we can have xi.
Yes, for every chart we have xi, and that is why sometime you will see that people say that this is a coordinate neighborhood of P, because it gives a coordinate system. And also you can see that people write a coordinate neighborhood like this.
Yes.
U is
Because it is a locally equivalent space.
it's a local.
That's supposed to be.
Exactly. So this is how local coordinates are defined on a manifold. Okay.
So we can consider it as an advantage by
Yes.
considering manifold
Yes.
We have this thing also. So if
Yes.
you want to study something for a larger space,
Hmm.
so manifold has
Locally.
all these things.
But there is only one problem. The problem that will emerge, suppose P is a point and its coordinates are xi around uxi. So this means I will say x1p, x2p, etc., xnp. You will say these are the local coordinates of the point P.
Yes.
Now what will happen, that this point may belong to some other coordinate neighborhood also. Let us say V.
B.
V is another coordinate neighborhood which contains P. And suppose the coordinate of V are, coordinate system around V is something yi.
Yes. Okay.
Now you will say that y1p, y2p, etc., ynp, they are the local coordinates of the point P.
Yes.
So now you have got two coordinates of a single point. And not only this, all points lying in this shaded part
They will have
will have more than one coordinates. There may be many neighborhoods containing P, and therefore there will be many coordinates of the point P. Is it right? So this is a situation. How to deal with this situation, that I will be telling you when I will impose a differentiable structure on the manifold.
this coordinate system is related to the neighborhood.
Yes. Okay. So what we expect that these coordinates must be related with each other.
Yes.
There must be a relationship.
Some relation there.
Okay. That we will explore. Rn में तो ये होता है कि हर कोऑर्डिनेट्स, हर पॉइंट के कोऑर्डिनेट यूनिक होते हैं, कोई वहाँ पे प्रॉब्लम नहीं.
That is not related actually. So here we have to say it is related to the neighborhood. They are infinite neighborhoods for a point.
Yes.
So there will be existing.
और क्या होता है, वहाँ भी थोड़ा आता है दिक्कत, इस तरह की प्रॉब्लम वहाँ भी आती है. फॉर एग्जांपल R2 में आपके पास कार्टेशियन कोऑर्डिनेट्स भी हैं जो कि ग्लोबली अवेलेबल हैं, और पोलर कोऑर्डिनेट्स भी हैं. लेकिन अच्छी बात यह है कि आपस में रिलेटेड है.
Related.
Once they are related, so you can go from one system to another in a smooth manner. Geometry doesn't change. Many things don't change. ऐसी R3 में आपके पास तीन तरह के कोऑर्डिनेट्स हैं. कार्टेशियन है, स्फेरिकल कोऑर्डिनेट हैं, सिलेंड्रिकल कोऑर्डिनेट. सो ऐसे इन जनरल सरफेस के ऊपर पैरामीट्रिक कोऑर्डिनेट्स हैं. ठीक है. सो ये कर्वलीनियर कोऑर्डिनेट्स हैं. तो कोऑर्डिनेट्स तो एक से ज़्यादा होते हैं, ग्लोबल भी होते हैं, यहाँ पे लोकल है. ठीक है. ओके. ऑल राइट. The next thing that I will talk about, yes, now transition maps. So let me consider a manifold. So I will talk of, first of all, transition maps. So let us suppose there is a manifold M. It has an atlas A. So M is a n-dimensional manifold. And it has an atlas A. So A is an atlas whose members are these charts U alpha, phi alpha. Alpha is ranging over some index set I. Now consider a situation, suppose U alpha is this neighborhood which is homeomorphic under the homeomorphisms phi alpha to an open set phi alpha U alpha in Rn. Okay, suppose this is phi alpha U alpha. This is a subset of Rn. And there is another neighborhood U beta also. The neighborhoods, there may be intersecting neighborhoods, many neighborhoods will be intersecting. So suppose this is one U beta from the same collection. I have one U beta and which is homeomorphic to another open set under the homeomorphism, say phi beta. This is homeomorphic to this neighborhood phi beta u beta. Now, since they have a non-empty intersection, let me shade this non-empty intersection part. So, this shaded region is in fact u alpha intersection u beta. This shaded region is an open subset because these two are open. So, intersection of open is open. So, this shaded region under the homeomorphism phi alpha will be mapped to somewhere here. Is it right? So, this shaded part is in fact phi alpha of u alpha intersection u beta. So, this part is also an open subset of Rn. Similarly, this shaded part will be mapped to this part in Rn under phi beta. Is it right? So, this part is phi beta of u alpha intersection u beta.
Yes.
This is also open because it is the image of an open set under a homeomorphism. Same thing over here. So, I have got two open subsets in Rn.
Yes.
This is one open set of Rn, this is another open set of Rn, and so I can think of this map between the two open subsets of Rn. This map you can see will be what? It will be this map. आप यहाँ से यहाँ आना चाहते हैं तो फाई अल्फा इन्वर्स से आप यहाँ पहुँचेंगे और फिर फाई बीटा के थ्रू यहाँ आ जाएंगे तो आपको ये मैप मिल जाएगा. अब आप ऊपर की सिचुएशन को भूल जाइए और ये सोचिए कि मेरे पास एक मैप है फ्रॉम वन ओपन सेट ऑफ Rn टू अनदर ओपन सेट ऑफ Rn. नाउ आई कैन आस्क माई सेल्फ इफ दिस मैप इज डिफरेंशिएबल. ओके, डिफरेंशिएबल के ऊपर भी ज़रा मैं अभी और बात करूँगा, लेकिन पहले ये बता दूँ कि वेन एवर देयर इज़ ए intersection between two coordinate neighborhood, there will always be such a map available to this. And similarly, I can think of this map also from here to here.
Yes.
This map will be phi alpha composition phi beta inverse. So, whenever u alpha intersection u beta is non-empty, there is a map, कहाँ से कहाँ तक? phi alpha of u alpha intersection u beta. There are maps, not there is, there are maps. From here, let me call it phi alpha phi beta composition phi alpha inverse. This is an open subset of Rn. Reason I explained to you, and it will go to, it will be phi beta of u alpha intersection. I am talking of this map. Okay. And this is also an open subset of R. And the other map will be phi alpha composition phi beta inverse. This will be a map from phi beta of u alpha intersection u beta to phi alpha of u alpha intersection u beta. Whenever this is non-empty, there are maps. अगर वो empty है तो आपको एक trivial map मिल जाएगा. ठीक है, कोई इंटरसेक्शन हो ही नहीं रहा तो ये मैप ट्रिवियल हो जाएगा, तो वो ट्रिवियल हो जाएगा. सो वी हैव these maps are called transition maps. These maps are called transition maps. So transition maps are available only when there is a non-empty intersection between two coordinate neighborhood. ओके और जैसे कि मैं अभी कह रहा था कि जैसे ही आपके पास Rn से Rm के बीच में मैप आती है, आप हमेशा उसको एक्सप्लोर कर सकते हैं, क्या ये डिफरेंशिएबल है, क्या ये कंटिन्यूअस ही है खाली, वगैरह वगैरह। ये सवाल आप अब पूछ सकते हैं और उसको चेक भी कर सकते हैं। लेकिन मैं इसकी डिफरेंशिएबिलिटी के में जाने से पहले एक आध बात और कर दूं जो शायद पहले कहने से रह गई। If you have, so let me discuss this thing over here in a corner. If you have a map, say F, from an open subset U of Rn into R, let this be a map. Okay. We say that f is a function of class CR if all partial derivatives of f up to order R exist and they are continuous. So, be a map. We say, let me write down the definition. We say that f is a function of class CR if all partial derivatives of f up to order R, up to order R exist and are continuous also. And are continuous. ठीक है, तब हम कहेंगे ये फंक्शन ऑफ क्लास सी आर है, या शॉर्ट में बोलेंगे तो आप कहेंगे कि ये सी आर फंक्शन है। ठीक है, अब मान लीजिए इससे एक कदम और आगे बढ़ते हैं और नाउ आई कंसिडर ए फंक्शन एफ फ्रॉम यू ऑफ आर एन इनटू आर एम। ठीक है ना, ये सिचुएशन में यू हैव सीन दैट f हैज़ गॉट कंपोनेंट्स f1, f2, f3, fm, वेयर ईच कंपोनेंट इज ए फंक्शन फ्रॉम u to r. Okay, now if each I running between 1 and m is a function of class CR, is a function of class CR, we say that, यहाँ लिख देता हूँ, capital F is a function of class CR. ठीक है, तो जब आपके पास Rn to Rm कोई फंक्शन हो तो आप हमेशा ये सोच सकते हैं कि ये CR क्लास का फंक्शन है और R क्या है। ठीक है, अब मैं थोड़ा जो मैं बात कर रहा था वो इससे पहले वो फर्स्ट ऑर्डर डेरिवेटिव तक की डिस्कस किया है। अब मैं हायर ऑर्डर में चला गया और हायर ऑर्डर में जैसे आएंगे उसके अंदर ये नई नई चीज़ें पैदा हो जाएंगी। अब मान लीजिए कोई फंक्शन है जिसके सारे पार्शियल डेरिवेटिव सब ऑर्डर के एग्जिस्ट करते हैं फॉर एवरी आर बिलोंगिंग टू एन। ऐसा भी तो हो सकता है, ऑल पार्शियल डेरिवेटिव ऑफ एफ एग्जिस्ट अप टू एनी ऑर्डर। तो हम कहेंगे कि एफ इज़ ए फंक्शन ऑफ क्लास सी इन्फिनिटी। एंड कंटिन्यूस, ये आपने अच्छा सवाल पूछा, अभी मैं इसके ऊपर बात करूँगा। तो हम उसको कहेंगे कि f बिलोंग्स टू सी इन्फिनिटी क्लास, और जिसका दूसरा नाम है स्मूथ फंक्शन। और कुछ लोग इसको खाली डिफरेंशिएबल फंक्शन भी कहते हैं। ठीक है, ये पॉइंट जो आपने रेस किया ये अच्छा पॉइंट है, इसके ऊपर ज़रा सी बात हो जाए। मेरे ख़्याल से ये बच्चों ने लिख लिया, ठीक है ना। आई कैन रब ऑफ दिस पार्ट, आई होप बच्चों ने लिख लिया होगा। ओके, अगर वन वेरिएबल का फंक्शन हो तो ये सब सी आर वी आर वाली बातें नहीं एक आती। अब मान लीजिए एक दिमाग में वैसे किसी को डाउट आ सकता है कि अगर पार्शियल डेरिवेटिव आर तक का एग्जिस्ट कर रहा है, आर ऑर्डर का एग्जिस्ट, और इससे पहले वाला आर माइनस वन ऑर्डर का भी डेरिवेटिव एग्जिस्ट कर रहा है और कंटिन्यूअस है, अगर ये कंटिन्यूअस है और डिफरेंशिएबल है ये, तो डेरिवेटिव हायर ऑर्डर का एग्जिस्ट कर जाएगा। ऐसे यहाँ पे, ऐसे यहाँ पे, ऐसे यहाँ पे, तो फिर ये बोलने की क्या ज़रूरत है? अगर मैं खाली ये कह दूँ कि आरएथ ऑर्डर का पार्शियल डेरिवेटिव एग्जिस्ट कर रहा है, तो पीछे वाले तो कंटिन्यूअस होंगे ही ना। ये डाउट आ सकता है, तो ये कहने की क्या ज़रूरत है? ऐसे नहीं कहा जा रहा है, समझा? तो ये एक सोचने की बात है। मेरे ख़्याल से मैं अभी इसको एक्सप्लेन नहीं करूँगा, अच्छा होगा कि बच्चे इसके ऊपर ख़ुद से सोचें और इसका जवाब मुझे बताएं, ठीक है? कि वाई वी इम्पोज कि ऑल ऑफ देम शुड बी कंटिन्यूअस ऑल्सो। अगर आर ऑर्डर का एग्जिस्ट कर रहा है तो इसका मतलब पिछले ऑर्डर का कंटिन्यूस तो तभी तो एग्जिस्ट कर रहा है। तो ये कहनी ऑल आर कंटिन्यूस, वी आर, यस। और ये मैंने एम्फसाइज की कि वन वेरिएबल के केस में इसी तरह कहते ही नहीं, कभी नहीं कहते कि पिछला डेरिवेटिव कंटिन्यूस भी हो। अगर आर ऑर्डर का डेरिवेटिव एग्जिस्ट कर रहा है तो कर रहा है, पीछे वाले की बात ही नहीं करता। तो मैं सोचता ही हूँ कि इसके ऊपर लड़कों को थोड़ा सोचने का टाइम दिया जाए। तो दिस इज़ अ गुड फूड फॉर थॉट। ओके, ऑल राइट। हाँ, मैंने शायद यस यस कुछ एग्जाम्पल्स भी आए। हाँ यस, सो वन शुड कीप ऑन थिंकिंग ना। अगर मेरे पास एक एटलस चूँकि यहाँ पे है और हमेशा जब जब नॉन एम्प्टी इंटरसेक्शन हो रहा है, ट्रांजिशन मैप आ रहे हैं, दो ट्रांजिशन मैप फॉरन इमर्ज हो जाते हैं, तो आई कैन डिमांड दैट एवरी टाइम वेन एवर यू अल्फा एंड यू बीटा their intersection is non-empty, I will demand that these maps are functions of class CR. If it so happens that every time the transition maps are functions of class CR, I will say that my atlas A is a atlas of class CR. It's a differentiable atlas of class CR. So this is the definition. If the given an atlas A, given an atlas A, let me write down U alpha phi alpha, on an n manifold. N manifold means n dimensional. On an n manifold M, if all transition maps are functions of class CR, are functions of class CR, we say that the atlas A, is an atlas of class CR, is an atlas is a differentiable atlas of class CR.
In atlas of class CR also we can say.
और CR atlas. अभी तो पूरी बात लिखें. We say that the atlas A is a differentiable atlas. Of class.
So transition maps are differentiable, then we will say ना.
डिफरेंशियबल और उससे भी ज़्यादा ऑफ क्लास CR. एक ऑर्डर तक के डिफरेंशियबल नहीं है, हायर ऑर्डर के डेरिवेटिव भी इसके एग्जिस्ट कर रहे हैं अप टू ऑर्डर R. ठीक है. और अगर C इन्फिनिटी ऑर्डर तक के एग्जिस्ट कर रहे हैं तो फिर हम उसको कहेंगे कि इट्स ए स्मूथ एटलस. ठीक है. ये बात मैंने सिर्फ बोल दी है, लेकिन इसको भी लिख लेना चाहिए कि इफ़ ट्रांजिशन मैप्स आर C infinity maps, then we say the atlas is a C infinity atlas. If the transition maps are C infinity map, the atlas A is called a C infinity atlas, called a smooth atlas or a C infinity atlas. दोनों ही टर्म यूज़ होते हैं और कभी कभी इसको डिफरेंशियबल एटलस भी बोला जाता है. सो दिस इज़ द मीनिंग ऑफ ए डिफरेंशियबल एटलस. ऑलराइट. अच्छा, अब जो एग्जाम्पल आपके हाथ में हैं वहाँ पे चेक करिए कि कौन से एटलस जो हैं वो डिफरेंशियबल एटलस हैं और कौन से नहीं. यस, RN से शुरू करिए. हाँ, यस. तो वहाँ तो आसान है. RN का केस तो सबसे ट्रिवियल केस है क्योंकि वहाँ पे एक ही चार्ट है, तो इंटरसेक्शन भी है उसका और होम्योमॉर्फिज्म भी आइडेंटिटी है. तो जो ट्रांजिशन मैप आया वो एक ही आया, आई कंपोजिशन आई इनवर्स, दैट इज़ ऑल्सो आइडेंटिटी. आइडेंटिटी मैप ऑन RN इज़ ए C इन्फिनिटी मैप. सो वो तो इस आपको सर्किल का और स्फीयर्स का और GLNR भी RN स्क्वायर का केस हो गया. तो बस सर्किल और स्फीयर ही रह गए, तो वो चेक कर लेना चाहिए. और सम अदर एग्जाम्पल आई विल डिस्कस लेटर. मेरे ख़्याल से बच्चों को मुझे बताना चाहिए कि क्या मेरी स्पीड कहीं ज़्यादा तो नहीं हो गई, क्या वो चाहते हैं कि मैं कुछ ज़्यादा लिखूं या कहीं कुछ गैप्स हैं तो उनको चाहिए कि वो मुझे इंडिकेट करें. ऑलराइट. अच्छा, ओके. तो आई स्टॉप एट दिस पॉइंट. And there are some other important things that I will discuss in my next lecture. Okay, stop.